Now we know from the first few listings we made of coin flip outcomes that whatever n is, h of n1 seems to be equal to n. And there's actually a pretty simple reason for that, and it's pretty easy to understand. So there's just, if you flip 4 coins, there are 4 ways to get exactly 1 head. If you flip 5 coins, there are 5 ways to get exactly 1 head. Now that follows from the numbers we have here, if you think about it, because h of 5, 1, you could get 1 head, or you get no heads on the first 4 flips, and then a head on the last one. Well, they'll give you 1 way to get 1 head on 5 flips. Or you could get 1 head on the first 4 flips, which can occur in 4 ways, and match it up with a tail on the last flip, giving you 4 additional ways, giving you 4 plus 1, 5 ways. Now we want to actually prove that h of n1 equals n. Now we first observe, and we're going to accept this, that h of n0 equals 1. No matter how many heads you flip, there's only 1 way to get 0 heads, and that is to get n tails. Okay? There's only 1 way that can happen. So we're going to be able to accept this. So if we got 1 coin, then we know that there's exactly 1 way to get no heads. That's to get a tail. We're only doing 1 flip. It's either a tail or a head. So 0 heads corresponds to tail. There's just 1 way for that to happen. 1 head corresponds to heads on the 1 coin, and there's 1 way for that to happen. So we're going to accept this as our starting point. And then we're going to reason on forward. Okay, well, h of 1, 0 equals 1. h of 1, 1 equals 1. So, well, that tells us that h of 2, 1 is 1 plus 1 equals 2. By the same reasoning we used up here. We're either going to get a head or a tail on our second flip. If our first flip was a tail, then we have to get a head on the second flip. And there's just 1 way for the first to get a tail. And otherwise, we get a tail on the second flip. And that matches up with the 1 way we can get exactly 1 head on the first flip. So we're just kind of using the same argument here. Now, we can also say that we know that h of 2, 0 equals 1 because of this. And we're not saying anything profound here. We're just saying there's only 1 way to get no heads when you flip 2 coins. That's to get 2 tails. Now, we know then that, and let me fix something here. We know very well that 1 and 1 is 2, not 0. Just thinking ahead, looking over at one of the zeros, I think. Okay, so we know that h of 2, 1 is 2. There are 2 ways to get 1 head when flipping 2 coins. And then there's 1 way to get no heads when flipping 2 coins. Well, putting these together, we can say that h of 3, 1 has to equal, well, the 1 way we can get no heads in the first 2, match that up with a head on the third flip, and the 2 ways there are to get 1 head on the first 2, match that up with the tails on the first flip. So that's going to be 1 plus 2 equals 3. Now we know that h of 3, 0 is 1. So if I had a little more room at the end of the board here, I could put these 2 things together, and I could get h of 4, 1, and so on. And I could keep going in this manner. And I would always get 1 more from here, and this number from here. The number is going to increase by 1. The number is going to increase from whatever this number is by this number, no matter what we do. Now that's not good enough for a formal mathematic argument, but that pretty well convinces us that it's true. So, I'm going to say this. Assuming h of n 1 equals n, we can conclude that h of n plus 1, and I got ahead of myself with the parenthesis here. H of n plus 1 equals h of n 1 plus h of n 0, and h of n 1 is n, we're assuming that, and h of n 0 for any n is 1, so that's going to be n plus 1. Okay, well, what does this tell us? This tells us that we know it's true when n equals 1, and now we know it's true, if we know it's true for n flips, then we've proven that it has to be true for n plus 1 flips. Okay, this works for any number n. In particular, we could say it works if n equals 1. Now, we've already shown that it works for n equals 1, but now we can go back and we don't even have to say this or this. All we have to say is, well, it's true when n equals 1, so it's true when n equals n plus 1, which is 2. Okay? So it's true when n equals 2. Now, since it's true when n equals 2, we come back here, well, let n equal 2. Then we know that h of n plus 1, which is h of 3, 1, is n plus 1, well, that's 2 plus 1, that's 3. So now, h of 3 plus 1, 1, is h of, well, h of 3 plus 1, 1 is 3 plus 1. So h of 4 plus 1, 1 is 4 plus 1. We've proven this for all values of n. This is called mathematical induction. If we've got a place to start, and we know we can always make the next step, then we assume we can keep going forever, and it's true no matter what the value of n is.